Okay. So on Tuesday, I tried to motivate the idea that we can use the calculus of variation to find the stationary value of an integral. So we want to find y of x such that the integral I, which we'll write as an integral from a to b, so it's a definite integral, of some function L that depends on y of x, on y prime of x, so dy by dx, and potentially on x. So we want to find the function y of x such that this integral is stationary. Okay, and I give you a physical example of an application where you might actually want to do that. So for example, the Brachistochrone. So this is what is the shape of the wire between 2 points, so that if you have a bead sliding down the wire, it gets there in the shortest amount of time. And we found that in that case, the time for the bead to go from a point on the wire to another point on the wire, so you have point A and point B, and you have a bead. The time for the bead to go from point A to point B, t, is given by an integral, so it would be the integral from xa to xb, if you want to be specific. So it's the integral from xa to xb, which is what we showed last time, of 1 plus y prime squared divided by the square root of 2g times ya minus y dx. Alright, so here's exactly an example of a problem where we want to find the function y of x, so the function of the wire that describes the shape of the wire, and it's given by finding the stationary value, so in this case a minimum of an integral that depends on y and its derivative with respect to x. So what is ultimately the condition to find y of x? So ultimately we want a differential equation that gives y of x. So the whole formalism we're going to develop now is how to take this integral, or the integrand L, and manipulate it so that we can get a differential equation that we can solve, and it would tell us y of x. Okay? Any questions about that general idea? All right. I feel like it wasn't too much material last Tuesday to go over. So. All right, so let's start doing this. Right. So now we want to work with L to find the stationary values of the integral I. So let's begin with the summary. So consider first. So I'm always going to call capital L the integrand, so the function of y and y prime of x, and I the integral for now. So consider the variation of L. So delta L which will depend on y, y prime, and x. I'm going to stop writing that y is really y of x, okay? But do remember that y and y primes are a function of x, and x is the independent variable. So as you remember, when you do a variation, the independent variable does not change. So the variation of L is defined as the varied value. So it's L when you evaluate y at y plus delta y, y prime plus delta y prime, and then x you don't vary, minus the unvaried value of L. So it's L value of y, y prime, and x. So using Taylor series, we can expand the first term. We're just rederiving the chain rule. So L of y plus delta y, y prime plus delta y prime, and x is equal, roughly through a first order Taylor series, so I'm going to expand using a Taylor series evaluated at y, y primed, and a small distance delta y prime away from that. So the Taylor series gives us L at y, y prime, and x, plus di L by di y, delta y, plus di L by di y prime, delta y prime. Okay? And at this point, we can almost treat y prime as a separate function, right? We haven't used any properties now that y prime is really the derivative of y. So it's almost like a separate function. All right, so that gives us so the variation is the second term minus the unvaried term, right? So the second term, the second equation here has the unvaried term in it. So when you take the variation, it drops, right, from the minus sign up here. And then you're left with only the partial derivatives. So this tells us that delta L, which is what we knew from the chain rule, and we'd already actually described this exact thing, delta L is di L by di y, delta y plus di L by di y prime, delta y prime. So if we consider now the variation of the integral, delta I, so that's equal to delta of the integral from a to b of L of y, y prime, and x dx. So if you recall, we showed that the delta operator commutes with an integral, so I can bring that in. That's equal to integral from a to b of delta L dx, and that's equal to integral from a to b, writing in the partial derivatives, di L by di y delta y plus di L by di y prime delta y prime dx. Okay, so that's the integral that we want. We haven't said anything yet about requiring it to be stationary. We've only written down the variation of the integral. Okay? So recall, we can write that delta y is epsilon phi of x, so we can write it as a finite function. Remember, delta y is the change in the function y of x to a new function. So it's the function that we want, y of x, plus epsilon times some small function of x. And hopefully this will give us a condition on y of x. Now we can also write So here epsilon is small, right? We can write delta y prime. That's delta of dy by dx, right? And remember, delta commutes with the derivative as well. That's the same as d by dx of delta y. That's the same as d by dx of epsilon phi of x. And epsilon is a constant number, so that's the same as epsilon phi prime of x, where phi prime is d phi by dx. Okay? So let me put that into our integral. So let's write the variation delta I. Let me factor out the epsilon. So we have the integral of di L by di y. And now the delta y, I factor out the epsilon, and I'm left with the phi of x here. And I have plus di L by di y primed. Same thing with delta y prime. I factor out the epsilon, and so I'm left with phi prime of x dx. So the key point here is that for a stationary point, let's put stationary point in quotations, because stationary point here means a specific choice of y of x that makes I stationary. So for a stationary point, we must have that the rate of change of the integral with respect to epsilon equals to 0. So that's like saying d by d epsilon of delta I equals 0. So if it's a stationary point, the choice of epsilon matters less, because we're at a flat point of the integral. Okay? So the rate of change of delta I with respect to epsilon is d by d epsilon of delta I, and d by d epsilon of delta I, given what you have above, is just delta I over epsilon. So it's the integral itself. So we require that the integral from a to b of di L by di y phi of x plus di L by di y primed phi primed of x equals 0. Okay? So it turns out we can work with this integral. So this is the integral of a sum, so it's the sum of two integrals, right? So let's look at the second part. So the second part is a to b integral of di L by di y primed phi primed of x dx. So now do you remember how to integrate by parts? If you recall, the integral of u dv is uv minus integral v du, right? let me try to use the phi prime as du and the L as v. So if I integrate this by parts, I have the uv term, so that's phi of x times di-L by di-y prime. So that would be evaluated from a to b. And I have minus the integral of, so now I need dv. Like I say, sorry, I wrote it the other way around compared to the example. So that's dv, that's u. Right, so now I need the integral from a to b of v, which is phi of x, and then du, so it's the derivative of di-L by di-y prime. So it's d by dx of di-L by di-y prime. Okay? So that's the integral by parts. Now recall, the variation at the endpoints must be 0. What does that mean? So let me plot out again what we mean by a varied function, right? So we have y of x so this is the true y of x. Alright, our equations hopefully will tell us that that is the correct y of x. But we also have a varied y of x. So this varied y of x, at any point on the line, the difference between the red line and the black line is epsilon phi of x. Right, so this is the varied y of x. And so what we see here is that, if we call these point A and B, we have a constraint that the endpoints are fixed. We just want to consider different possible functions, but they still have to end up at A and B, just like our wire, right? We can bend the wire into all sorts of different shapes, but the whole point of the problem is that it has to be fixed at the 2 points. Otherwise, you can choose whatever wire you want, and you just make a vertical wire. What this tells us is that phi at xa is equal to phi at xb is equal to 0. Or in other words, delta y equals 0 at the endpoints. So if I rewrite now my integral, delta I over epsilon, so that was the integral from A to B. We had a di-L by di-Y phi of x. Then we had the part that we did by integrated by parts. So we had what did we have? We had a phi of x di-L by di-Y prime. Let me be explicit here. The integral ends here, right? So this part here is evaluated from x a to xb, and then minus the integral of phi of x d by dx of di L by di y prime dx. So this middle term here, that came by parts, is equal to 0. Because phi evaluated at xb equals phi evaluated at xa equals 0. So our integral becomes the integral from a to b. So I was going to write it as one integral. Note that both integrals have a phi of x in them. So I'm going to factor out the phi of x, and then from the first integral I have di L by di y, and from the second integral I have minus d by dx of di L by di y prime. And that's got to equal to 0. Now remember, this phi of x is an arbitrary variation from the true function, the black one, to some arbitrary red one that we sort of use for testing. But we require this integral to be 0, and that's got to be regardless of our completely arbitrary choice of phi of x. So this must be 0 regardless of our choice for phi of x. So this integral must be 0 regardless of the choice phi of x. Only way for that to be possibly true is if the other thing in parentheses is identically 0. So the thing in parentheses must be equal to 0, and since the thing in parentheses is equal to 0, I'm going to write it the other way around. Because minus 0 is equal to 0, right? So I'm going to write the thing in parentheses the other way around. So what I mean, I'm going to write it as d by dx of di L by di y prime minus di L by di y equals to 0. Okay. And let's box this. This is by far the most important equation in the whole course. You will know it by heart soon enough. It has a name. It's called the Euler-Lagrange equation. So this equation, so the EL equation, the Euler-Lagrange equation, is a differential equation for y of x. And we'll see that maybe we have another sequence now with doing the exercises and examples. But we'll do a bunch of examples where we will find these differential equations. So to go back to the Batista-Crone problem, the integrand is the function L, right? And so you can see if you take di L by di y, you get something with a bunch of y's and y primes. Same when you do d by dx of di L by di y prime, you get a bunch of y's and y primes. and then those will be equal to 0. So you have an equation that's going to relate y's and y primes and other things to 0. And so that is a differential equation, right? So in principle, then one can solve it. So this is a very important condition. So now the strategy is in fact quite simple for solving these problems. If you know the function L, it's just a matter of applying the chain rule and writing out the Euler-Lagrange equation. And that will give you that differential equation that we seek for y of x. So any question about that? So let me just point out in mechanics so in analytic mechanics T is the independent variable, and we typically would like to know Qi of T, which are the functions describing how the generalized coordinates evolve with time. So in that case, we'll find that our function L will be a function of our generalized coordinates, so Q1 to Qn, Q1 dot to Qn dot, and T. So the Qi dots are velocities, and then the Q1 to Qn are the coordinates. So when we do classical mechanics, we'll have basically the same math, but our independent variable will be t instead of x, and so anything that was a y prime, so a d by dx, will be a dot, a d by dt. And so in analytic mechanics, we will want stationary values of some integral which we'll call s instead of I. And it'll be the integral from some time a to some time b of whatever this function L is. And so this is, in the example we ran through, we only had one function y, right? We had y and y prime and x. So here it's like having multiple y's, so like a y1, a y2, and a y prime, 1 prime, and x. And so you'll show in the assignment that when you do this, you end up getting one Euler-Lagrange equation per degree of freedom. You get one Euler-Lagrange equation per degree of freedom. So you'll get d by dt of di L by di qi dot minus di L by di qi equals 0. So that'll be 4I equals 1. Yeah. And so we haven't worked out any of the specific math, how this relates to classical mechanics, but you can see sort of the framework that we're going to get. You have a system, and you can describe the position of the system using these generalized coordinates. You would like to know how these generalized coordinates evolve with time. And so the supposition here is that there is some special function L that you can write that's a function of the coordinates and their velocities, whatever this function L is. We'll see that it's called the Lagrangian. But if you can write this special function L, then you can automatically find the differential equations that describe how the coordinates evolve with time by using this Euler-Lagrange equation. So it'll be a rather simple process for solving any mechanical system, that you have to write out this function L, but then after that it's just math to get the differential equations that describe the coordinates. And it's just math to solve them. Okay, so it's actually a very, very powerful way of doing classical mechanics. And we'll see that this function L of the coordinates and the velocities is what's called the Lagrangian. That's why we're using the letter L. And it can be found by using the kinetic energy and the potential energy of the system. But I think we'll get to that in a couple of weeks. So any questions about that? The Euler-Lagrange equation? Okay. So let's look at a special case now. So this is the special case what if L does not depend explicitly on X? So what I mean is that L is a function of y prime, but not X. Previously we had L as a function of y prime, and X. But maybe L doesn't depend explicitly on X. So it depends implicitly on X, remember? Because y is a function of X, right? So if you change X, L does change. So the test to say that L does not depend explicitly on X is to say the partial derivative of L with respect to X is equal to 0. So that's a special case. In fact, we've already seen that special case, or at least it's come up, but we haven't solved it. So in the case of the brachistochrone, if we look at our function L here, L depends on y. You can see the y is in there, right? It depends on y prime. You can see the y prime in there. But it doesn't depend on X. There's no explicit dependence on X. It's implicit, because y, of course, is a function of X. But it's not explicit. So if you do the partial derivative of the integram there, of L, with respect to X, you get 0. So that's what I mean by L by X, or by L not explicitly depending on X. I mean L by X is equal to 0. Okay? So this brachistochrone is in fact a case when L doesn't depend on X. So it turns out the Euler-Lagrange equation simplifies when that's the case. So to show this, or to find out the simplified version of the Euler-Lagrange equation when L doesn't depend on X, consider the following identity. for no particular reason, except that it gives the right answer, what if you were to take d by dx of y primed di-L by di-y prime minus L? Let's say you just want to do that. Okay, so this is just a matter of taking the derivative. So it's d by dx of a minus b, so it's going to be a prime minus b prime. So the a term has product rule, right? There's two functions of x in there. There's y prime and di-L by di-y prime. When I do d by dx of the first term, I have to use the product rule. So if I use the product rule on the first term, d by dx of y prime is y double prime, di-L by di-y prime, and then I have plus y prime d by dx of the second term, d by dx of di-L by di-y prime, and then the last term minus dl by dx. Alright, let's write that out. So that's equal to, leaving the first terms unchanged, I have y double prime di-L by di-y prime plus y prime d by dx of di-L by di-y prime. And then I have dl by dx. So L is the principal function of y prime, and x. But we'll remove the x part in a second. So if I write the total dl by dx, using the chain rule, I have di-L by di-y, dy by dx, plus di-L by di-y prime, dy prime by dx, and then plus di-L by dx. But of course we said that di-L by dx was equal to 0. So if I write this out now, notice, well, let me just write it with primes first. So I have y double prime di-L by di-y prime. So the first two terms I'm going to write unchanged, plus y prime d by dx of di-L by di-y prime, and minus di-L by di-y, and I have dy by dx, that's called y prime, and then I have minus di-L by di-y prime, and then dy prime by dx is y double prime. So you can see that the terms with the y double primes cancel, right, the first and the last term. And so I'm left with y primed, which I'm going to factor out. So the two middle terms, the two terms in the middle both have a y prime, right? So I'm going to factor out the y prime term. And so that's going to be d by dx of di-L by di-y prime minus di-L by di-y prime. Now remember, we're finding the stationary value of an integral of L with respect to dx. Regardless of whether L depends on x or not, if the integral is stationary, then L satisfies the Euler-Lagrange equation. Right? And the Euler-Lagrange equation is precisely the fact that the thing in parentheses here is equal to 0. So this part here in parentheses is equal to 0 by the Euler-Lagrange equation. So this whole thing turns out is equal to 0, because 0 times y prime is 0. So that means I'm going to rewrite the term on the left. d by dx of this sort of arbitrary combination, y prime di-L by di-y prime minus L, that thing is equal to 0. So d by dx of the thing in parentheses on the left here is equal to 0. So what is true when d by dx of something is equal to 0. So not the partial derivative, right? This is the total derivative d by dx. So if d by dx of something is 0, something doesn't depend on x, right? To say that the derivative with respect to x is equal to 0 means that the thing is actually constant, at least with respect to x. Okay? So since d by dx of the thing in parentheses here is equal to 0, we have y prime di L by di y prime minus L equals a constant. And so this is actually more simple than the Euler-Lagrange equation. This is still a differential equation for y of x. So this is a more simple differential equation for y of x. By more simple, I mean than the Euler-Lagrange equation. So the situation is always that you want to know y of x, and that integral must be stationary. You can always get the Euler-Lagrange equation to give you the differential equation for y of x. But in the case where the integrand did not depend explicitly on x, this might be a more simple way to solve the problem. In fact, once we start doing mechanics, and L is the Lagrangian, it turns out that this equation here, that this y prime di L by di y prime minus L equals a constant, is actually conservation of energy. So that constant is the total energy of the system. That's something that we'll see further on, and I'll remind you of this, what we did today when we get that. That's it. This sort of obscure math now with absolutely no applications that I've shown you yet, leads to conservation of energy, very fundamental things in classical mechanics. But I want to get the math over with so that when we go into classical mechanics, we can just refer to these results. I don't have to show that the thing is a constant. I can just evaluate that constant and we'll find that it's energy. All right? Let's do well, it's not really written as an example in the notes, it's just the next section. But it's kind of this practice with this sort of math. What about the case when there are multiple functions? So what if L is a function of y1 of x all the way to yn of x, y1 prime of x, all the way to yn prime of x, but does not depend on x. So that's in classical mechanics, when we have the q's, again we have multiple q's, multiple q dots, and we could potentially have an L that doesn't depend explicitly on t. So here we have an L that depends on many y's and doesn't depend explicitly on x. So if I write out dl by dx, so the total derivative of L with respect to x, then we have di L, the chain rule for everything that L could possibly depend on. So it's di L by di y1 times di y1 by dx, dy1 by dx, so y prime, plus di L by di y2, y2 primes, plus di L by di yn primed plus di L by di y1 prime, y1 double prime plus etc. di L by di yn primed, yn double primed, and then the last term would be a di L by di x, but that's equal to 0. So I can write this a bit more compactly with the summing notation. That's the sum from I equals 1 to n of di L by di yi primed plus di L by di yi primed yi double primed. So if we redo now the same derivation, knowing what dl by dx is, so remember when we had only one function, I considered what is d by dx of y prime times di L by di y prime minus L. In the case when there's multiple functions, we consider the following identity. So it's again d by dx of some arbitrary looking term. And the arbitrary looking term is the sum from I equals 1 to n of yi primed di L by di yi primed minus L. So the sum is only of the terms with i's on them, right? L is the total. So if I do this, again, I can bring the d by dx inside of the sum, right? The derivative of the sum is the sum of the derivatives. So when I bring the d by dx into the terms that are summed, then I have to have a product rule for each term, right? So I'm going to have, bringing it into the sum, I equals 1 to n. Now I just apply the product rule to this term here. So the first term, if I take the derivative, it's yi double primed di L by di yi primed, and then it's plus yi primed d by dx of di L by di yi primed. And minus d by dx of L, so it's minus dl by dx. So because we have this dl by dx here, that's why we just spent a few minutes earlier to write out what dl by dx is with the sum. Okay? So we can now plug that in. So that's equal to the sum from I equals 1 to n of, rewriting the first two terms unchanged, so I have yi double primed di L by di yi primed plus yi primed d by dx of di L by di yi primed, and then minus the dl by dx. So the dl by dx we wrote as a sum as well, from I equals 1 to n of di L by di yi primed plus di L by di yi primed yi double primed. Looks like there's a mistake in the notes. that term there, if you're following in the notes, the absolute last term has n's instead of i's in it. Okay, so again, I can put this all into one sum, right? And when I put it all into one sum, you can see that the first and the last terms cancel because of the minus sign. And then the two middle terms both have a yi prime in them. So that's going to be equal to the sum from I equals 1 to n. Let me factor out that yi prime that all terms have. And then I have d by dx of di L by di yi primes minus di L by di yi. Okay, that's exactly the same argument. Each function yi of x satisfies the Euler-Lagrange equation if each function y of x satisfies the Euler-Lagrange equation. The term in parentheses here, well, let's call them brackets because they're nested. The term in brackets is 0, so this whole sum ends up being 0. So now, to go back to the top of the equation, we have d by dx of this sum, yi prime di L by di y prime, minus L. D by dx of that thing is equal to 0. So if d by dx of something is equal to 0, then that thing is a constant. And so what we find is if di L by di x is equal to 0, that was our initial condition, right? Then the sum from I equals 1 to n yi prime di L by di y prime, yi prime, minus L equals a constant. So again, once you do classical mechanics, we'll find out that this is exactly how you find out the energy of a system given the function L. And so indeed, energy is conserved. But of course, right now that's completely arbitrary statement. But do remember this, or hopefully it will be helpful to remember this when we get to the part with classical mechanics. All right, so any questions about that derivation? All right. In the final section, when we're done with all this math, well, that's not true. There's still a lot of math in this course, but at least it'll be tangible. So the final section here is the stationary value of an integral subject to auxiliary conditions. Now, auxiliary conditions is just a different way of saying constraints. All right, so if we go back to our brachistochrone, we had no constraints. You had an infinitely long, or you had an infinite supply of wire that you can stretch from A to B to make the bead go as fast as possible, and you must choose the shape of the wire that just makes that happen. But maybe you have a constraint. Maybe the wire, you only have a certain amount of wire. So not only does it have to be the fastest, but it has to be with the amount of wire that's given. Or maybe the wire has to go around an obstacle or whatever. So you could see how potentially you could have a constraint involved. Okay? So it's the same thing. You still have to find the stationary value of the integral, but then you're not allowed to just choose any random function. There's constraints between the functions. Okay? So let's do stationary value of an integral subject to constraints. I don't know why I put an arrow there. More like a new section. And so just to make things confusing, let me use the notation of classical mechanics rather than that of mathematics. So what I mean is I'm going to make t, I'm just notation-wise, right? So I'm just going to call the independent variable t instead of x, and I'm going to call the functions q's instead of y's. But it's really just a relabeling, okay? So let's use notation from classical mechanics. So we'll use t instead of x, and we'll use qi of t instead of y I of x. All right. So then the Euler-Lagrange equation in this case would be d by dt, I think we already wrote this earlier, of di-L by di qi dot minus di-L by di qi equals to 0. Okay. So we use qi of t instead of y of x, and then also we use qi dot instead of y prime I. Okay. This is just to give you more practice, understanding the way how to do the math, right? But then also because when we do classical mechanics, you can just copy and paste the results, and it'll already be with the right function name. All right. So our problem is want stationary value of some integral I, which is the integral from a to b of L, which depends on q1 to qn, q1 dot to qn dot, and t. So that's the same as before, so now it's subject to k constraint equation. So just like in the case of when we're doing a stationary value of function subject to constraints, I'm going to write my constraint equations as an equation that relates the variables to each other. So the first one will be a function of the q1s, q2, all the way to qn, potentially t, equal to 0. So these are the constraint equations. F2, Q1, Q2, all the way to Qn, T equals to 0, all the way to Fk of Q1, Q2, Qn, T equals to 0. Alright, so just writing it this way, just think of these as equations that relate the Q to each other, right? So it could be like Q1 plus Q2 equals 0. That could be one of the F equations. So in principle, right, you could use these constraint equations. So let's say the first equation, F of 1, is Q1 plus Q2 equals 0. Then you know that Q1 is equal to minus Q2. You can go up in your integral and you can remove all of the Q1s and replace them by minus Q2s. Right, so you could just use these constraint equations to go and eliminate k of the coordinates in the integral, and then you end up with n minus k for the Lagrange equation. And so maybe that's good enough. Maybe you're happy that now you only have n minus k differential equations to solve rather than n. But that could be a little bit arbitrary because maybe you're describing a system of particles, and no one particle is more important than the others, and you want to know how all the particles behave, and you don't want to treat one particle preferentially over the other particles, so the other particles will be jealous, and so maybe you want to find a method that treats them all the same. And so you want to have to make an arbitrary choice of saying the coordinate of this particle is a dependent coordinate and this particle here is more independent, because that would be arbitrary. Okay? So just like the same situation occurred when we're trying to find the stationary value of a function. So you can guess that the method is called the method of Lagrange multipliers, and it's very much the same idea that we just did for the function. So let's do it for the stationary value of an integral. So could eliminate k of the qi, but that may be arbitrary. So can use the method of Lagrange multipliers. So the method of Lagrange multipliers. First, we need to consider the variations of the constraint equations. So delta F1 would be equal to, by the chain rule, di F1 by di Q1, delta Q1 plus di F1 by di Q2, delta Q2, all the way to di F1 by di Qn, delta Qn, and that there's no term with a delta t, right, because t is the independent variable. And so since F1 is equal to 0, then the variation of F1 is also equal to 0. And so that will be the same all the way down to delta Fk. So that's di Fk by di Q1, delta Q1 plus di Fk by di Q2, delta Q2 plus di Fk by di Qn. So it's di Fk by di Qn, delta Qn equals to 0. So we can construct a new functional So remember, functional is just a fancy word for saying an integral of which we want to find stationary value. So consider delta I as written a bit strange in the notes. There's a delta L missing. So consider a new functional, the integral from a to b of delta L dt plus the integral from a to b of the sum, so lambda 1 delta f1 plus lambda 2 delta f2 all the way to lambda k delta fk dt equals to 0. So we've already done the delta L part to show that it's equal to 0, right? And so then I'm adding a bunch of lambda I times delta fi, and those delta fi's are all equal to 0. So I'm basically adding a linear combination of zeros to my initial thing that was also equal to 0. Okay, so we've already worked with the first term to get the Euler-Lagrange equation, right? So the first term is going to look something like integral from a to b d by dt di L by di qi dot minus di L by di qi times delta qi dt. Alright, and when we defined the Euler-Lagrange equation, at that point we then said delta qi was equal to epsilon phi of x. Take the epsilon out, so it's delta I over epsilon, and then it has to be 0, and so then you end up with the term in brackets equal to 0. Right, so that delta qi, we were using epsilon phi I of x. And then we said that part of the integral must be 0 regardless of what choice phi of x we use, and so the term in brackets must be identically 0. So that's not true anymore now necessarily because we have the second term in the integral, the term with lambda delta x. So if I look now at the lambda 1 delta f1 plus lambda 2 delta f2, etc. So that's the terms that I wrote up here, right? I wrote for delta f1 and for delta fk. So I can group these terms, right? Those are going to be a di f1 by di q1 delta q1, a di f2 by di q1 delta q2, and so each of the f's from f1 to fk is going to have a delta q1 term, they're each going to have a delta q2 term, and they're each going to have a delta qn term. So I can factor them out and rewrite them in terms of the delta qi terms. So we can say that the integral from a to b of the lambda 1 delta f1 plus lambda k delta fk dt, we can write that by factoring out the delta q term, delta qi term, so that it's going to look something like, a sum. Oops, there should be a sum up here too. So the second term here, the dot dot dot, I can write that lambda 1 delta f1 as the sum from I equals 1 to n, oops, of lambda 1 delta f1 plus lambda k delta fk delta qi dt. So if I write both terms together, I can write delta I as the sum from I equals 1 to n, the integral a to b of d by dt of di L by di qi dot minus di L by di qi plus lambda 1 di f1 by di qi plus lambda k di fk by di qi delta qi dt. Okay? So what we did earlier, when we were doing the Euler-Lagrange equation, we didn't have all the lambda terms in them, and we effectively said that the delta QIs can be varied independently, and so you can choose whatever phi of x you want, or phi I of x, because in this case there's multiple ones, and so then the term in brackets should be 0. Okay? Now, in this case, where there's these constraint equations of the S, the delta QI, both the little thing there before the dt, they're not independent of each other. So if I change delta Q1, I cannot change independently delta Q2. The two of them might be linked. So I can't just say all the delta QIs are free to vary independently, so the whole thing in brackets must be 0. In this case, you can't vary them independently. Some of the delta QIs have an influence on the other ones. Okay. So in this case, because of the constraint equation, cannot vary delta QI independently. So what we do is we choose the lambda I, or the lambda 1 to lambda k, such that the last k terms in the sum have the thing in brackets equal to 0. Namely, we choose the lambdas such that the term in brackets, I'm going to write the term in brackets, d by dt of di L by di qi dot minus di L by di qi plus lambda 1 di f1 by di qi plus all the way to lambda k di fk by di qi equals 0. And so that's for I equals n minus k plus 1 all the way to n. So that's the last k terms. So you've chosen the lambda I so that for the last k terms, the thing in brackets is equal to 0. So if you now rewrite the integral, the full integral with the sum in it, then you only need to write the sum up from I equals 1 to n minus k, because the last k terms are identically 0. So now you write the terms only from I equals 1 to n minus k, but now you only have n minus k delta qi's in there. And so now you can vary them independently. So for these first I equals 1 to n minus k terms, the delta qi's can be varied independently, and so then the term in brackets is then equal to 0. So then for the first n minus k terms, the delta qi can be varied independently. And so then you get that for the first n minus k terms, then the term in brackets is equal to 0. So for those terms, d by dt of dial by diqi dot minus dial by diqi plus lambda 1 dif1 by diqi plus lambda k dfk by diqi equals to 0. And that's for I equals 1 to n minus k. And so, of course, that was the whole point of the Lagrange multiplier method, is that these two equations for the last k terms and the first n minus k terms are in fact identical. Right? And so it's true for all terms. All terms satisfy exactly the same thing. Okay? So then these are the same for I equals 1 to n. That was the whole point, the whole genius of this Lagrange multiplier method. And so then this equation is satisfied for all I. So let me write it a little bit neater. Let's go to the next page. Hence we have for all I, we have d by dt of dial by diqi dot minus dial by diqi minus the thing with the lambdas equals to 0. So let me move the lambdas to the other side. So then I have minus lambda 1 df1 by diqi minus dfk by diqi. Oops, lambda k. So let me write that with this little sum sign here. So we have d by dt of dial by diqi dot minus dial by diqi equals to minus the sum from j equals 1 to k of lambda j dfj by diqi. And let's introduce a final piece of notation. So that's equal to d by dt of dial by diqi dot minus L by di Qi, and I'm going to call that equals to capital Qi. So I've introduced capital Qi to be minus the sum from j equals 1 to k of lambda j di fj by di lowercase qi. So the box equation, the term on the left is exactly the same term that appears in the Euler-Lagrange equation. So in the Euler-Lagrange equation, that thing is equal to 0. In the case where there are constraints, that thing is equal to this capital Qi, and this capital Qi is a function of Lagrange multipliers and the constraint equation. And so remember, needs to use the constraint equations to get rid of the lambda I or j. So you have n equations here, and then here you have another k equation. So you have n plus k total equation to solve for the differential equations of Qi's and the unknown Lagrange multipliers. Alright, so that's quite a lot of material to do in one lecture. So this equation that we got, let's say that they're like the Euler-Lagrange equation. So I was gonna stop here for today. There's an example at the end of the notes. The idea of that example is just to show you that it's a little bit annoying that we have this minus sign here in the capital Qi. So this minus sign here is because we moved the lambdas up here from one side of the equation to the other. But I could have very well, when I introduced the lambdas in our linear combination, I could have said they were all minus lambdas. And so then we can completely choose the lambdas. So that example just says, if instead of doing L plus lambda 1 F1, lambda 2 F2, I had done L minus, that way when I moved into the other side of the equation, it would have all been pluses. Okay, so since the lambdas are completely arbitrary, I think that's just trivial to show. Okay, so we have found our goal, at least mathematically, is how to find the differential equation for the functions so that an integral is stationary, and we've done that both in the case that are unconstrained and constrained. So are there any questions? Alright, so I was going to stop here today. And then Tuesday I haven't decided if we'll continue with the lecture or do the examples, but I think we will continue with the lectures, and then Thursday we'll do a whole bunch of new examples. I'll remind you that the assignment is due tomorrow. And the assignment should be scanned and uploaded to Moodle. Okay, so if there's no questions, we'll stop here. Thanks, everyone.